Hello, everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken at University of Albany and his brother Joel Chaiken. We're here to help you see how to learn how to approach SAT math questions. Here's a math question. You can see, calculate a section. This is a double question. So then let's do this one. We'll do both. We'll do both 22 and 23. So, we have a formula. At a large distance off from radio antenna, the intensity of radio signal is related to the power of the signal P by the formula above. That's sort of like from physics. Seth knows. Seth got a degree in physics from Cooper Union, right?
Yeah.
Yeah, so you learned about that in college. And maybe
This is the so-called inverse square law.
Right, exactly. Good. Which of the following expresses the square of the distance from the radio station in terms of the intensity of the radio signal and the power of the signal? So this is what they normally call a literal. You have to solve r squared.
Yeah.
So it's not that hard. There are two ways to do it. You can either cross multiply or multiply both sides by pi r squared. How should we do it? Should we cross multiply or should we multiply both sides by
Well, let me show you how I thought of it, and then you could add another couple of ways of doing it.
Sure.
What I did was, this is what I thought of. This is how I thought of it.
Mm-hmm.
I equals, and I didn't write this down. What I thought of was simply take this term and take this term.
Yep.
And interchange them.
Right. That's a good fast way to do it. Yeah.
To get. So I put I in the denominator. Which ones have I in the denominator? Well, the only one that has I in the denominator is this one.
Wow, you can really,
checks.
Yeah, you can actually do that really quickly just by looking at the only one that has an I in the denominator.
That's right. Yeah.
Yeah. So there.
But you have to check. But if you use that strategy, you have to check the rest.
Right. There's so many different ways.
But again, given that there's only one choice with I in the denominator, you could make the assumption that one of the choices in every SAT question is the correct. That the questions are not faulty.
Obviously.
Yeah.
Obviously.
Okay.
Yeah.
So that's how I thought of it.
Right.
But of course, perhaps you could remind how to what they would say prove that you could.
That's right.
Carry out this swapping.
Exactly. In other words, you never justified
and solve as a way of solving for r squared in terms of everything else.
Yeah, you didn't justify what you just did.
No, it's a skill in algebra. I know, you could always swap like that.
Yeah.
But then, a similar property. If you have, general. A equals BC over DE. You could take the E and put it over here. So you get EA equals BC.
Yeah.
Do stuff like that. You could put the D over here too and get DEA.
Okay, so why don't you erase
you could put the A down here and get one. That's so instead of thinking, hey, multiply both sides. That's an extra step in thinking and calculating. Some math teachers would teach you to multiply both sides by the same thing, to see what happens in order to prove that this is mathematically valid. But after you've proved it to yourself and know that it's valid, you could just do the manipulation. That's quicker, and you get it's quicker, and you get the right answer.
That's true. That's true. So
Yeah,
people who have a lot of experience would do it that way. But we do
yeah,
need to show, in all honesty, and just to be complete, because some people may not have this much. Don't forget, there are going to be people taking this test who really are liberal arts people, and
yeah,
they
yeah,
just survived math, or they never really got it. So they really should try it to do it also the
yeah,
more traditional way. So Seth, can
yeah.
you just do a
Well, this is
backstage?
again. It examines, in addition to your knowledge, it also examines your fluency.
Yeah. Well, no fluency only even because you're on a time constraint, right?
Yeah,
If
and
yeah,
you're in a time constraint. Yeah,
Okay, so let me just show the other two
and so it
possibilities.
doesn't hurt. It doesn't hurt. It doesn't hurt, and it helps. It helps if you're doing the SAT practice questions. You discover that what our videos may help is help you discover where you could use some practice to develop fluency
Right,
in addition to knowledge.
right,
And
absolutely.
indeed, the SAT curricula, the materials published by the College Board say that it does test fluency.
Aha, so they sort of are expecting
Oh
you
yeah,
to do this question very quickly.
fluency doesn't hurt,
Fluency doesn't hurt,
and it's
but
cool
just okay. But let's say
as
you
long
don't
as
have
but
Seth.
correctness is prior to fluency.
Right, but Seth, let me show how you do it if you don't have the same fluency you had. You can multiply both sides. You want to move the r. You want to get that r squared by itself, and it's in the
Yeah,
denominator. So you would multiply both sides by 4 pi r squared I is equal to p. Right? You put a 4 pi r squared here, a 4 pi r squared here. These cancel. You get this, and then you solve for r squared. R, so you divide both sides by I 4. But at this point, actually, if you realize that you're dividing by this, you could almost see that the only answer is going to be one where an I is in the denominator,
yeah, yeah,
and
yeah.
you can
No,
go from there.
I mean, I would do it. I would do it a bit quicker. Start with, start with, what you did. I equals P over 4R squared. Multiply both sides by R squared.
Right. Yes. Right. Yeah.
The R
That's right.
squareds
That's right.
cancel,
That's right. That's right. That's right. That's right. That's right.
right? And then divide both
Yeah.
sides by I.
Right. And the other thing to do is cross multiply. You could also cross multiply
No,
these.
no, no, I wouldn't do that.
No, but you could. You
You
could.
could,
You could.
okay. Let's see how hard it is. You cross multiply, big deal. So you
Well,
get
then you cross
cross
multiply, you get
multiply,
this.
you
You get
get
that.
4 pi R squared times I
Yeah.
equals P,
Yeah.
and the R squared is horrible. It's still stuck.
I know. I know. I
It's
know.
still it doesn't help too much. Here R squared has 3 neighbors.
Yeah. Right.
Cross multiply, the R squared still has 3 neighbors.
I know. But Seth. At this point, you can do this calculation in your head and then see that the only answer has the I in it. Right? You can sort of look at this and say which is the only one that. Which sorry, Seth. You don't like me to write things over anything, so I'll be more careful.
Okay. Well, I still recommend to our audience to think about it the way I do.
Yeah. No. That was a really good efficient way to do it.
Yeah.
Okay.
So recommendation. Do it like me, not my
It's a little
brother.
obnoxious, but that's fine. So that's okay. Okay.
Yeah.
Okay.
Okay.
Not
So
everyone thinks like you. Everyone thinks differently. So we have to go all, we have to open up, people. Right, yeah. Just hopefully you get that right. But this question you should be able to do after practicing. You should be able to question like that in maybe what 12 to 14 seconds, something like that.
yeah.
Okay. For the same signal emitted by a radio antenna, observer A measures the intensity B 6 times the intensity measured by B. The distance of the observer from the radio stations is what fraction of the distance of observer B from a radio station? Oh, wow. This teachers love this question. Oh, this is like the most unbelievable. They love this question. Immediately if you're used to this question, you know it's the square root of 16. So it's either 4 or a quarter, because you take the square root of 16.
Okay,
but let's do it more methodically.
But no, 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 no. It's well, with the R in the denominator, we see that the closer you are to the transmitter, the smaller is R and the higher is the intensity. And then, and of course, it's natural. It's a radio with a radio broadcasting thing. Naturally, if you're closer to the antenna, you get a more intense signal.
Right.
And so it's going. So let's see. You measure the intensity to be larger by 16, and so you have to be closer.
Right.
And in fact, they only give you 4 choices, and the question is the fraction of the distance. And the way I thought of it is I used my experience in physics to say, well, it's the inverse square law, and so it's the amount of intensity change is the square of the distance change.
Right. Yeah.
And we're interested in the distance change. So what number among these is the square of 16 is 1/16 is the square of what number here? That's a quarter.
Right. That's so. Yeah, I was able to do it too. Just thinking about that, but just knowing how popular a question like this is. Normally, you see it like this. They'll say the radius is doubled, right? Radius is doubled. Radius is doubled. How much does the area go up? By what factor does the area go up? The area is pi r squared. So if the radius is doubled, the area goes up by 4 times. That's typically.
I was if I were making, I can make the question harder versions. A harder version.
Yep.
I think a harder version would put a 4 for C and a 16 for D.
Right, exactly. Yes. Now, of course, we really haven't shown anyone how to really do it. Okay, we just sort of waved our hands and used the fact that we actually know how to do this problem. But that doesn't really help people. Let's do it a little bit. Maybe we should do a little more methodically. Okay, but
all right, do it more methodically.
But how many people? Because this question here is the hard version of this, and most of you have seen this type of question in school. So how do you do this a little bit more methodically? Yeah. So let's see. You want to draw a little picture, maybe. So observer A here is 16 times bigger. 16 times, like a big number, times the observer of B, and B is over here. Wait, my Xport froze. Hold on. We have to wait 6 agonizing seconds. B is going to be further away from the antenna. So this is the distance, and B is going to be over here, right? So this is 16 times B, right? That's what they said. Observer A, 16 times B. So Seth's right. A is going to be closer because it's an inverse relationship. The distance of observer A from the radio antenna is what fraction of the distance from observer B? So this distance is, I don't know, what do you want to call this? D, right? So then
I'll use the lowercase d because R is a lowercase.
Okay, so then let's use the lowercase d. So that distance is d. We want to know what this distance is. This is dB. How about that? dB. That's better. That's dB. We want to know what dA is, right?
Right.
So what we do is we want to know the ratio of dA to dB or dB to dA. What's the rate?
The distance to A, distance of A, dA, is what fraction of the distance to B? So it's dA over dB.
Exactly, dA over dB. Hey, look at this. look at this. We already have this. Wow. So that means we have this relationship, but r squared. R squared
Yeah.
is dA squared. So,
Yeah.
what do? We do d.
Yeah.
Oh, look at this. Oh, this comes right out. So we can square both sides. This is dA squared over dB squared, right?
What? That's garbage. What?
Yeah,
You
that is
just
garbage.
no, that's garbage.
That is garbage. That is garbage.
Don't make a mistake. There we go.
Yeah. So dA. Wait, no, but if you. I'm starting to crash. But the P. The P is the P is the power.
Is
the
constant.
P is the power. No, the P is 16 times. So.
Well, the P in the formula is constant.
No, the intensity is 16 times.
Yeah.
The P isn't constant between dA and dB.
No. In the formula, P is constant. The intensity at the observer is what's variable. Yeah. You said P.
Isn't P the intensity?
P is the constant that's in the formula. P is the power at the antenna.
Oh.
So if you use P for the density at the observer, you're going to be really confused.
I am really in trouble. Oh, it's this one. Oh, it's I. It's I.
Yeah.
Okay, so let's. Wow, it's a real mess here. So, God, this is really not going well. So, it's really hard to do this like a little more methodically. You got a mess.
Well, if using the result from the last question.
Yeah.
Let's use the same variables. dA. I'm going to call dA RA. Don't erase it.
Okay.
And the distance to observer is capital A, because the observer is A.
Right.
And the distance to observer capital B is RB.
Right.
And you're interested in the distance of A to the distance of B.
Right, exactly.
So what you're interested in is RA divided by RB.
Right.
Well, the answer. Okay, I'm going to write it like I did. Here we go. Well, scratch paper. If you take the answer B, applied to A, and applied to B separately. Let's apply them separately. R sub A squared, right?
Right.
Equals constant P squared over 4 pi intensity
A.
At A.
Exactly. That's where I was heading.
And R sub B squared,
right,
equals P squared divided by 4.
Actually, it's 16 pi.
Hold
those
on.
are all going to cancel. Those are
P
16
squared.
pi.
No, don't think that yet. Divided by intensity sub B. Well, we're interested in RA over RB.
Right.
But we have formulas for RA squared.
Right.
Over RB squared.
Right.
So let's simplify RA squared divided by RB squared.
Right.
And we could see the P squares cancel.
Right.
The 4 pi's cancel. And what we have is 1 over IA, the reciprocal of IA.
Right.
Divided by the reciprocal of IA divided by the reciprocal of IB.
Exactly. That's right.
Now multiply both the top and the bottom by IA times IB.
Or it's a complex fraction. It's a complex fraction. It equals
Yeah, yeah,
IB over
yeah.
IA.
So various we could say a fluent way is to recognize by a rule for playing with complex
That's
fractions
like a
is
must
that
know. Okay, you must
that's
know that.
that.
You must. You really got to know that.
And so the square of the answer equals IB divided by IA.
Exactly.
IB divided by IA, well, IA is 16 times bigger.
Right.
So IB divided by IA equals 1/16.
Right.
That equals the answer.
Squared.
The answer, ANS is the answer.
Right.
Squared.
Right.
So what? So I don't like to even think of square roots here. I'm thinking what is the number whose square is 1/16?
Yeah, it's a quarter.
And that's a quarter.
That's a quarter. That's a quarter.
So
that's, right.
rather than saying, hey, what's the square root of 1/16? I don't think that way. I think, well, what number squared equals 16?
Yeah,
which is what the square root is.
Yeah, but it's the same
But
thing.
to find the square root, you have to somehow guess what number squared equals 1/16, and that's a quarter.
It's the same thing at that point. You're home free. You're home free.
Yeah.
You're home free. Now, I don't know how many people followed us on that. I certainly crashed on that, but this is what I was getting to before when I said R squared over RB squared, because you have a formula. Notice we both made small mistakes. Seth squared the P. That's completely wrong. Remember, I said 16 pi squared. That's also completely wrong. But we still came through and got the right answers. This is, again, typical. We all make mistakes. You have a P squared. That's completely wrong. You know, when you square R squared, you don't do a P squared. You don't square the P.
I didn't square the P.
Yes, you did. Yes, you did.
No, I didn't.
Yes, you did. What is that? What is that? What is that? What is that? What little thing is that? P squared.
What?
You wrote that.
Oh, I did. Mean over here?
Yeah, when you said it, you wrote P squared because your brain was like trying to square things. Yeah.
I
That's
did.
your handwriting. Yeah, you made a little mistake. But I did.
Oh, I did. Yeah. Okay. Yeah, I did. Yeah.
But I also, but when you were doing it, Seth, go back to the video. I said 16. Seth, you forgot to change that to a 16 pi squared. I was also wrong. Okay, so we both, when you do math, it's okay to be wrong. Just you still actually got the right answer. But you see, we're a little messy. But followed us.
So
here.
I actually wrote P squared there.
Yeah, because your brain was squaring things. Yeah, but I
yeah, sure. It's that's what we do. Make mistakes.
Yeah, that's what we did.
But the big picture I had about that was that P was in this problem. P is constant.
Yeah, P's cancel. P's cancel.
Well, they cancel and they're constant. Therefore, they cancel because they're constant.
They cancel because
they're constant over applying the formula to observer A and observer B.
Right.
They're constant because the observers are observing the signal from the same radio antenna.
Right. Yeah.
And that the radio antenna has a particular value of power.
Yeah.
Okay. Yeah. Wow. Okay. There we go. Blunder, mistake.
But now I'm just wondering. I wish we had live feedback of this thing, because Seth, can you just erase? I feel like we probably should do this a little neater. Just because this question comes up so much, Seth, can you just erase all the red stuff?
Okay.
Let's do this a little bit more like neater so people see, because this question does come up and why
did that happen?
No, you erase your. Oh, Seth, you have to do it. Go forward on the thing. Go forward. You erase too much. Go forward.
What? I think backward.
Go. Use the arrow. God.
The arrow to go forward?
Yeah, because you erased the whole thing. You erased the whole test. You erased the whole test.
Oh well, sorry.
Yeah, so go forward a little bit. Yeah, keep going. Yeah, stop. I'll tell you something. Maybe we'll just move the whole thing. Okay?
Yeah.
Let's just do it over here, okay? So let's do this incredibly neatly, only because this question comes up so much. Okay, you have to compare. You have to compare basically. What is it? You have to compare like when the radius doubles, how much does the area go up? You have to compare.
Yeah.
You
Yeah.
have to
Yeah.
compare the output of a
Okay.
function when the input changes. So this is how you do it,
Yeah.
right? Okay, so you have R, you define RA and RB. Then you have a formula. RA squared divided by RB squared, because that's what they're asking for. That's the answer, right? So what you do is you put names on it. PA, 4 pi, IA squared. It's not IA. It's not IA squared. I almost made the same mistake. PB, 4 pi, IB. And I'm not squaring things. That was a mistake. See, we're using this formula, right? We're putting little subscripts on everything. Okay, so this is PA and
Okay.
PB,
But
right?
shouldn't we recognize that PA equals PB?
Of course, you have to recognize that. Yeah, PA and PB are the same. PA and PB are the same. That because it doesn't change. The NBC is still broadcasting out at a megawatt or something. So
Okay.
it doesn't matter.
So rather than call them PA and PB, I'm going to call it's a antenna, the radio antenna. So let's call it. A is already used. So instead of PA, we're going to say the power of the radio. So I'll call PR
We have to go on.
over PR.
Right. Oh, right. That's right. Yes.
PR and PR are the same.
Yeah. Well, okay. So now all of a sudden this is fun because now all of a sudden a lot of stuff cancels. So these guys cancel because they're the same. The 4 pi's cancel. The pi's cancel, and then you're left with 1 over IA divided by 1 over IB. Use complex fractions to multiply by the reciprocal, and you get IB is divided by IA. And they tell you that you have to read carefully that IB is IA is 16 times bigger than IB. So that's 1 over 16. So to pull it all together, it's RA squared divided by RB squared is equal to 1/16. What is then RA divided by RB? And you see pretty clearly that this is a quarter.
Yeah, and that's what we did.
Yeah,
right.
So the way to do problems when things change, something changes, and you want to know what is the effect of the change. This is the way you generally set it up. You want to use subscripts, and then you put the formula in, and you'll see magic. A lot of stuff cancels, and then you really see the relationship. The key here is to use the subscripts if you want to do it methodically.
Okay.
Okay.
Right. Well, let me. Okay, good. So I want to make another remark about like changes in this example. So here's the other remark. Maybe could you scroll it so that we have some room on the left of the problem?
Yeah, look at that. We actually have a lot of real estate.
No, to the left of the problem.
Oh my God. See, I don't know my left and my right. That causes problems.
Okay. Yeah. So, the law of intensity and distance is intensity equals the power of the transmitter divided by 4 pi distance to the antenna squared.
Right.
So, what if we double the distance?
Okay.
So if we replace R by 2R, so let's do it this way. Let's so going to double the distance. What happens to I? Well, the new I equals P over 4 pi 2 times r squared.
Right. That's right.
The 2 is squared.
Right.
And so let's factor out the square of 2 and get 4
Right.
times 4. I'm not canceling. 4 pi r
Squared.
squared. P over 4 pi r squared is the original intensity.
Right. Exactly.
This is the new intensity. So the new intensity is 1/4 of the original.
Right. That's right.
So if R doubles, the intensity goes down by a factor of 4.
That's the easier question.
If R gets halved,
right.
the intensity goes up by a factor of 4.
That's right. So this is the easier question. This is the easier question. This is very similar to the pi r squared. You double area, you double the radius.
Yeah, exactly. Yeah.
Question.
Well, is it? No. This is the area. The area is proportional to the square.
That's right. Exactly. Yeah.
Here we have the intensity is proportional to the inverse of the square.
Yeah.
So it's not the same as the relationship between pi r squared.
But the method of doing it is the same.
No. It's again is so if we have I think what Joel was talking about is the area of a circle of radius r is equal to pi. What do you do? What's
okay. That was the Zeitboard went crazy. That's okay. Yeah, it's okay.
The area. What's going on?
Zeitboard sometimes goes nuts.
Stupid software.
Yeah, stupid software. Right.
Yeah, the is a different problem. The area.
It's a different problem, but it's done the same way.
No, it's not. No, what's different is the intensity is inversely proportional to r squared. Hold on, let me tell them this. The area is directly proportional to r squared.
Who cares? It's the same
method. I care. Yeah, it's very important to know whether it's it's inverse. It's inverse. To r squared versus direct to r squared.
I don't think you get the point. The point is that if you have area is pi r squared and r double is 2r, then you put pi 2r squared.
Yeah.
You get 4. And then you have pi r squared. But the pi r squared is a1, so that's 4a1. It's the same method. We're talking method here. We're not talking detail. See how
detail is important.
No, that's the detail of the formula. The method is the same. You put the thing in, then you see it's 4, then you have it's the same thing.
Yeah.
You see how the I here is the same, and he put it in here. I put the area in here.
So the same method apply. You're saying this is the same method that would apply to the
cubic relationship.
That would apply to the volume.
Yeah, of course.
The volume of a cube.
Yeah, of course.
Plus, they don't do 3-dimensional geometry in the SAT. The volume of a cube, whose side is s.
Yes, s cubed. Yeah.
Is equal to s cubed.
Right.
So if s doubles, the volume goes up by a factor of 8.
Yeah, it's done the same way. It's the same method. And then there's that. The other one, physics. What's that inverse relationship to the cubic? Isn't there some radiation thing, like heat coming out of a thing is like 1 over r cubed or something?
No.
Yeah, there's a 1 over r cubed thing in physics.
That's for moment.
No. Isn't there a radiation thing?
No, with radiation in 3-dimensional space, the intensity satisfies the inverse square law.
I thought there's a cubic. What about?
No. Because here's why.
Oh no.
In 3-dimensional space.
God.
The area of the sphere
Oh yeah, the surface area.
is proportional to the square of the radius. And
Right.
then the total energy at points a given radius from the emitter is the intensity time at the given distance times the area of the sphere.
Okay.
So since the area goes up by the square of the distance,
Right.
how the energy is distributed over the area, the intensity goes down
Right.
with the
Right.
square
Right.
of the
Right.
distance.
Right. The closer you are, the more radiation you
And
get.
that is the origin of the law that this problem is based upon.
And of course,
So what happens is, I draw a picture in blue. What happens is, in this problem, we have the radio antenna. There is observer A.
So we know.
Let's see. Hold on. Well, A is here.
So if anyone wants to go, you're welcome to go.
Hold on here. A is here, and what B is further away.
Yeah.
Okay. Here's what happens. Even though they're on the surface of the Earth,
God, now we're getting a physics lesson.
The signal goes out like this.
Right.
In a sphere.
Right.
Like that.
Right.
Okay.
Right.
And the same energy, same total energy, is distributed over these longer and longer lines. But actually, these are sections of hemispheres.
Oh God.
I can't really draw that. Imagine these are a three-dimensional view. These things would look like igloos, bigger and bigger igloos.
You're going a little like.
So that's the picture of this.
Okay. I mean, basically, the bottom line is when you use your cell phone, try not to keep the cell phone next to your ear because the radiation out of your cell phone could potentially, there are reports that radiation is not that great for you. But let's just finish off one quick thing that Seth alluded to that I just want to mention. And Seth, it was actually really important. And I'll ask Seth the question. How much debate do you think the people who wrote the SAT had where they would have, some of them said, oh, come on, we got to put 4 and we have to put 64 as answers here. And screw these. Or maybe screw the 256. So they had to. They had to have considered not using fractions, but using 4 and 64 there. Don't you think so? And then they debated it, and they said, no, let's make the question easier and not put those as choices. Jeff? Because then
it's secret. I have no idea. My guess is they have a way of that they have enough data to rate the difficulty of the questions, and then they choose how many questions of each difficulty level there shall be.
Oh wow!
And then they pick questions to fill in the difficulty levels, and then they and in each difficulty level they choose maybe a broad they try to make it broad diversity of topics.
Yeah, right.
So if they were making this question to be one of the more difficult ones, they would have used the more difficult choices.
Interesting theory.
But that's just my guess.
Yeah, we have no idea.
I'm not privy.
It's no idea. It's just interesting to sort of speculate But
Yeah.
I'm glad they didn't give these choices, because I would have had to think a little bit more carefully.
That's right.
Right? I
Yeah.
would have had to have thought more carefully. But knowing these choices, it's, with the experience of knowing, having done enough of these problems, it's simply a quarter. That's why both
Yeah.
of us were able to answer the question in a second. But that's only because we have a little bit more experience with this stuff
Yeah.
and with these types of questions. Because this question comes up so many times. Oh, God. So many times. Okay. I think that really is it. Today's 40 minutes. Oh, God. I'm sorry, everyone. But,
Bye.
hopefully you gave you some insight. You know how to do this type of question. It comes up so much. Okay, so have a great day. And then like us, dislike us, give us comments, and email us some questions to our email address at satmathquestionoftheday at gmail.com. Okay, have a great day, everyone. Bye.
Bye.
Bye.